Good afternoon, class. We are looking at intermediate algebra, practice test 4, module 4, chapters 8 and 9. Chapter 8 was covered. We are looking at chapter 9, exponential and logarithmic functions. Chapter 9, exponential and logarithmic functions. What is a one-to-one function? A function is one-to-one if each element in the range corresponds to exactly one element in the domain. In other words, if f of a equals f of b, then a must be b. If a is not equal to b, f of a cannot be equal to f of b. We use the horizontal line test to check if a horizontal line can be drawn so that it intersects the graph of a function at more than one point. The graph is not a one-to-one function. Find the inverse of this function and also check with FO f inverse of x. First of all, composite function. FOG is f of g of x. GOF is g of f of x, reminding everyone. To find the inverse, the process, there are a couple of different ways. One way is to start replacing f of x with y because it makes it easier to work with. Then we interchange the two variables x and y. We solve for y and we call it f inverse. So in this case, we're going to change f of x to y because it makes it easier to work with. Interchanging them, y becomes x, x becomes y. In this step, we already have the inverse. However, we don't stop there. We solve for y by moving the -5, which becomes +5, and then take a cube root. Now we give it the name f inverse. Let's check what is f o f inverse or f inverse o f. It ends up being x. You have to show that. So here's f o f inverse. Instead of x, we are going to put f inverse. This is cube root. This is being to the power of 3. They cancel each other. X plus 5 comes out. And then with -5, they cancel each other. You get x. F o f inverse is always equal to f inverse o f equals x for two functions that are inverse of each other. F of x is 2x minus 7. Let's change it to y. Interchange x and y. We're going to solve for y. And by solving, we move the -7 to this side, becomes +7, x plus 7 divided by 2. That is why we change the name to f inverse, and we are done. To check f o f inverse, we are going to look at f of x and replace the x with what we just found. F o f inverse of x is 2 times x plus 7 over 2 minus 7. These twos cancel each other. You get x plus 7 minus 7. 7 and -7 cancel each other. We proved that we've come up with the correct answer. Now, a big chunk of this deals with logs. So let me give you the synopsis of logs as follows. Log, if b is larger than 0 and b is not equal to 1, y equals log x base b is equivalent to x equals b to the power of y. Pay attention to what I have here. It really makes it easy to follow. If we look at these two, when we start with log, y equals log x base a is the same as x equals a to the power of y. Notice they both have the same base, namely a, and they both have the same exponent. So they have the same exponent, they have the same base. So we should be able to go from here to here. The methodology is very simple. If we put the y on this side with this arrow, and I will show you in a moment. So if you look at this one, a to the power of y is x, a to the power of y is x. Now, this is the general case where the base can be any number, and here's the properties you've seen. Log 1 is 0. That means it doesn't matter what the base is. Why is that? Because a to the power of 0 is 1. This is what I meant. If you look at this arrow, this makes it a to the power of 0 equals 1. That's the reason. And so this one, a to the power of 1 is a. These two refer to the fact that exponential functions and logarithmic functions are inverse functions. So in this case, when you have log base a of a to the power of x, in essence, they undo each other, they give us x. And in this case, you raise a to the power of log x with base a, they undo each other, they give us x. This is the product rule, quotient rule, power rule. Now the same thing for common log, the base is 10. We don't write the base 10. So basically don't write the base 10. In this case, you don't have to. In this case, you want to be careful, you write log 10. In this case, you write log 10 to the power of x is x. This one, 10 to the power of log x equals x. And finally, natural log, the base is e, the same thing happens. I know it's a lot, but we have been working on it for the past few weeks. I hope you're very comfortable with that. So understanding the general form, these two cases that are special cases make life easy. When we graph, because the exponential functions and logarithmic functions are inverse functions, they are symmetric with respect to the line y equals x. We also have this formula known as change of base formula. So this is the synopsis of what we have seen regarding logs. So if they give us this and say, okay, graph these two functions, and that's what we did. I want to show you how to graph to begin with when we don't know how the graph looks like. But ultimately, with practice now, we know the graph looks how in general as it was mentioned in the previous page. So go back to the previous page. Exponential functions when the base is larger than 1 looks like that, and logarithmic functions when the base is larger than 1. So we already have an idea based on the previous page, but how do you do that? Well, if you don't have any idea, you pick up pairs. So let's do that. If we choose x to be a bunch of numbers, for example, -3, -2, -1, 0, 1, 2, 3. Now 3 to the power of -3, that means 1 over 3 cubed or 1 over 27. To the power of -2, 1 over 9, so on and so forth. So this would be the value of y. And we can plot those pairs, we have the graph. The same thing happens for the log. In order for you to do the log, to graph the log, it is easier to rewrite it in this format and choose the y first. So let us choose the y. And it so happened, if you work it out, you get the answer that you got here as x. And that's another thing. Remember, when two functions are inverse of each other, their domain and range are changing, meaning domain of one becomes the range of the other. So look at this one. If you think of as a few pieces of domain here, look at a few pieces of range here. Because they both have the same base, namely 3, these two functions are inverse. One is exponential, one is log. And if you graph it very carefully, this is your exponential function, this is your logarithmic function. So here's the important parts as you look at the graph. Again, this is true anytime the base is larger than 1. It looks something like that. As you look at the exponential function, there is no x-intercept. Y-intercept is located at 0, 1. Domain are real numbers. Range, the positive one, from 0 to infinity. And you have this line, which is a horizontal asymptote, the x-axis or y equals 0, and the function is increasing. On the other hand, if we look at the log, let's see what happens. Now, see, we didn't have the x-intercept. Now we don't have a y-intercept. Y-intercept at 0, 1, x-intercept at 1, 0. I hope you see because they are inverse function. Domain was negative to positive infinity here. Range is negative to positive to infinity. And the domain is from 0 to infinity, like the range of the other. This one had a horizontal asymptote. Now this one has a vertical asymptote, okay, which is the y-axis x equals 0. Both functions are increasing. There is a lot here that I have covered, but again, we've been through that in the past few weeks. Now, I want to look at a lot of logarithmic examples which cover logarithmic properties. Some of them are identical to the questions we have seen. Some of them are similar because I want you to be exposed to various types of questions and even new ones. For example, log 81 base 3, log 5 base 25, log 0.001, which means base 10. Log 81 base 3 equals 4 because 3 to the power of 4 is 81. This is one way to look at it. Or a different methodology. I'll go over that in a moment. Log 5 base 25 is 1/2 because 25 to the power of 1/2 is 5. And log 0.001 equals -3 because 10 to the power of -3 is 0.001. What I want to go over is the methodology of finding it if you don't remember the numbers that easy. So for example, if you want to find this one, you say log base 3, 81 is x. Here's the arrow that I mentioned. 3 to the power of x is 81. You know 81 is 3 to the power of 4, makes it 4. If you look at the second case, log base 25 of 5, we don't know. Let's say this time we use a different variable. Let's say y. That means 25 to the power of y must be 5. We know 25 is 5 squared, so this becomes 5 squared to the power of y, or 5 to the power of 2y equals 5. The 5 on the right has no exponent. That means the exponent is 1. That means 2y must be 1, and y becomes 1/2. When it comes to common log, you look at the number of zeros. So if I give you log, if it starts with 1, 10,000, you see that there are 4 zeros, and that's your answer. On the other hand, in this case, 1, 2, 3 decimals, the answer is -3, or you can write it in this fashion. All right, let's write them in an exponential form quickly. Look at this arrow that I give you. 5 to the power of 4 is 625. 7 squared is 49. 1/3 to the power of -4 is 81. 81 to the power of 1/4 is 3. You can always check. 1/2 to the power of -5 is 32. If you practice with this, it really becomes easy. Let's try a few more. 5 to the power of q is m. This one, when we see ln, that means the base is e to the power of z is v. When we don't see a base, it's log, the base is 10. 10 to the power of t is w. So we have those. Now we want to go back and write them in a logarithmic format. So log of the right side, always log of the result. Log of the result, what is the base? 3 equals x. Log of the result, in this case, log of 8, but the base is e, so we get ln instead of log. So ln h equals k. In this case, log of the result, log b, the base is not 10, the base is 100. On purpose, I chose that because I want you to pay attention. This is not 10. So log b base 100 is 8. We want to expand using various properties. In this case, we're going to use the product rule. So log of each piece, log of x plus log of y plus log of z. Don't forget the base is 7. This one uses the quotient rule, ln of the top minus ln of the bottom. This one uses the power rule, 10 sits in front, and we are done. Now this one, you can do it in one shot, actually, or you can do it with a few steps. Quickly, you can write this as log of the top minus log of the bottom. The base, whatever it might be, we keep it intact. Now, the first can be dropped into log of a squared plus log of b to the power of 4. This one, you rewrite it, and the exponent in each case sits in front. We are done. This really can be done even in one shot, but take your time. All right, we are expanding or decomposing. First, we can write this to the power of 1/2. We put the 1/2 in front. And this piece is log of x cubed plus log of y to the power of 5. We bring the 3 in front, we bring the 5 in front, and don't forget there's a 1/2. So 3 in front times 1/2 is 3/2. 5 in front times 1/2 is 5/2. This is your final answer. This one is simply ln of the top minus ln of the bottom. There is really not much you can do, and you don't have to separate them because you cannot, the bottom cannot be separated. Again, you can do it in one shot. By the way, all of them, you always use the same base. In this case, you can write log base 4. Of the top, I'm going to write square root of x as x to the power of 1/2 and 10y as 10y to the power of 1/3. And minus log z to the power of 10, same base. Just keep on writing the same base, namely 4. The first piece can be cut into 2. The last one is very easy, and it's very straightforward. This part, we can write it as log base 4 of x to the power of 1/2 plus log base 4 of 10y to the power of 1/3. So therefore, this one would be 1/2 log x base 4. This would be 1/3 log 10y base 4 minus 10 log z base 4. Now 10y, we can separate it into 10 and y. Please understand this 1/3, by the way, let me just fix something here. This is 10y to the power of 1/3. Again, maybe just writing that one. This part is 1/3 log of 10y with base 4. And that's the answer. So this has a few steps. It's not too bad. Now we want to go the other way around. We want to combine them into a single log. It's just multiply 2x to the power of 4 times 3x to the power of 5 here. You get 6x to the power of 9. In this case, let me just write that and you simplify it. This one, you divide 6x to the power of 9 by x squared, and you write the simplified version, ln of that. Very straightforward. So what happens in this case, if I were to, I can get rid of the 2, put it here. I can get rid of the 3, put it here. So I have log of x squared plus log of x plus 1 cubed. I'm going to multiply x squared by x plus 1 quantity cubed, and I'm done. It is easier if we rewrite this as follows. So I'm going to write this as log x plus log z cubed minus log y to the power of 1/2 or square root of 1. The reason I'm putting these two together because plus means just multiply these two. So this gives you log of x z cubed. And this goes underneath. So I hope you can go from here to here. If you have a difficult time, do this too. Maybe I just write it for you. You can replace this with log of x z cubed and then combine it finally with negative log square root of 1. That's how you simplify this. A few equations quickly. If we look at these cases, they're fairly simple. In part A, notice they have the same base, so they must have the same exponent. Set the exponent equal. This is a very easy case. Minus 4x goes there, becomes positive 4x, and minus x is 3x. X becomes negative 1. I'm assuming from here to here, you can handle it. It's not a big deal. They have the same base, they must have the same exponent. In this case, they don't seem to have the same base, but we can change this such that everything has a base of 4. This is 4 cubed, this is 4 squared. Therefore, the left side is 4 to the power of 3 plus 3x. And therefore, 3 plus 3x equals 2. In other words, if you want, I can write this step for you. This is the same as 4 to the power of 3 plus 3x equals 4 squared. And you can move the 3 and divide, and you get x equals negative 1/3. I hope everybody is okay with that. Then write the part C, 7 to the power of x minus 10 equals 10. We know 1 equals any base to the power of 0. Because the base here is 7, we make it 7 to the power of 0, which means x minus 10 must be 0, in which case x becomes 10. Starting with part D, first divide by 2, then you just write the logarithmic format or take a natural log of both sides. Because this is base E, take a natural log. If I take a natural log, the left side becomes simply 3x, and the right side becomes ln of the right side. If I divide by 3, I get the answer. This is the exact answer, class. And of course, approximation, you use a calculator. Part E, move the 10 and it becomes negative. 4 to the power of x equals any negative number, has no solutions. It has got to do with understanding the range of exponential functions. When the base is a positive value, remember the range was 0 to infinity, so it can never be negative. As far as part F is concerned, if you can see that you can do it by factoring, or you can do it by substitution, letting e to the power of x be, let's say, y. If you go, then this becomes y squared, or just write it as such. So there are two ways to do that. You can let e to the power of x be, let's say, y. So it's y squared minus y minus 6. You do that just like that. Therefore, e to the power of x equals 3, e to the power of x equals negative 2. I hope you know that this has no solutions. This one, if I take a natural log of the left side, I get x. So x is ln 3. And again, this is an exact answer. This has no solutions. So precise answer, x equals ln 3. All right, how do we solve this? Anytime we have a log, a single log on one side, and a number on the other, all you have to do by definition. So by definition, 9k is equal to 3 squared. Just the definition. So k becomes 1. Anytime you have a bunch of logs and a number on the other side, put the two together. So I hope you realize you have to multiply 4 by negative 5x, you get log of negative 20x. So the left side, you combine them into a single log, and now you do the definition. There is no base, so 10 to the power of 2, which is 100. You know this is 100. 100 divided by negative 2, negative 20, it's negative 5. Now it's important to check. The arguments can't be negative. Minus 5x, negative 5 times negative 5 makes it positive. That's why it's okay. Anytime you have a log on both sides, then you don't have to move and make sure each side has a single log. Because this is a single log with the same base, they must have the same argument. So 5n minus 2 must be 8 minus 5n. I hope you realize if I move this one here, I get 10n. If I move this one here, I get 10, and n becomes 1. It's very simple. Understand the process. The left side is a single log. We are in good shape, but the right side is not. We multiply x by 12, and now it becomes a single log. They have the same base, namely 10, because it's a common log. They must have the same argument, namely x plus 12 equals 12x. Now, if I subtract the x, I get 11x. I divide by 11, x becomes 12 over 11. So again, I want to make sure everybody understands. If I cancel out the x, I have 11x on this side. Same thing, we are dealing with logs only. Therefore, we bring them to a single log. The left side becomes ln of x plus 4 over x. The right side doesn't change. They have the same base, namely e. They must have the same argument. We do the cross product. This is x plus 4. This is x times x plus 1, which is x squared plus x. Cancel out the x, and x squared becomes 4. Has two answers, positive as well as negative 2. So when we go back up here, negative 2 is not a problem here, but creates a problem here, so it's out. Same thing here. We have a bunch of logs. We combine them into one by multiplying x by x minus 1, which results in x times x minus 1 being 2 to the power of 1. This is x squared minus x, and this is 2, which we move it to the left because we want to do the factoring and solve. Results in x minus 2x plus 1 equals 0. This gives us 2. This gives us negative 1. We go back to the original function. Negative 1 makes the first one undefined, so that's out. You don't even have to check with the second one. Similar questions we've done, so we're going to go through them fast. 3 to the power of x 243. On the other hand, you know this is 3 to the power of 5, so x must be 5. 125 is 5 cubed, therefore x must be 3. Remember, 64 is 4 cubed. Let me erase that and redo that. 4 cubed to the power of x, that means 4 to the power of 3x. That means 3x equals 4x plus 1, and x becomes -1. This is slightly different. We want to have the same base. We don't have it. So what do? In this case, which is a little bit more complicated than the rest, you take a log of both sides, either natural log or common log, it's up to you. So if I take the natural log, then in this case, x sits in front, in this case, x minus 2. Now, it's important to know, I can change ln 4. It becomes a nasty decimal. I can change ln 9, the same thing. But if you keep it as such, it's an exact answer, but they are not missing. ln 4 is a number, so is ln 9. So let's distribute here. Because we are solving for x, we're going to bring everything involving x to the same side. It's easier to move this guy. Now I can factor the x out. If I divide the right side by the parentheses, I have the answer. There are two things I want to add. Number one, this is an exact answer. Number two, this is the same as saying 2 ln 9 over ln 9 minus ln 4. Take a look at what I'm talking about. You see this negative sign? If you take it down, becomes that, which means over here, when we were moving things, we could have moved it the other way around. Also, instead of ln, if you took log, common log, if you change this ln to common log, it gives you the same answer. In this case, log 2 and 3 and 5 are given with some base. We don't know the base. And we want to see if we can find log 50, log 5th root of square root of 300. All you have to do, look at those numbers 2, 3, and 5 and say, I want to factor this. All you have to do, factor this. I hope you realize 50 is 2 times 25 or 2 times 5 squared. Therefore, this is log 2 plus 2 log 5, same base, same base. I can't emphasize this enough. We know log 2, base A is A, and this one is C, therefore 2 of it. We do exactly the same thing. This is 300 to the power of 1/5. 1/5 sits in front. And number 300, first of all, every 10 is 2 times 5. So this is 2 times 5, 2 times 5, and 3. So you have 2 squared times 3 times 5 squared. I'm showing you factoring in a very fast manner. 10, remember 10 is 2 times 5. And therefore, if this is 2 times 5, this is the same thing, and this is 3, this is what we have. Now cut them into pieces. This is 2 log 2, this is plus log 3, this is plus 2 log 5. Don't forget the 1/5 in front. And replace each one based on what's given. We are done. 1/5 times 2a plus b plus 2c. Whether you distribute the 1/5 or not, it doesn't make any difference. We've seen this type of questions before, so we're going to go through it fast. Definition: 4 to the power of x is 16, and you know 16 is 4 squared. Therefore, x is 2. X is 2. The other one, 9 to the power of x is 27. We know 9 is 3 squared. So replace the 9 with 3 squared. So 3 to the power of 2x, and this is 3 cubed. Therefore, 2x must be equal to 3. And x becomes 3 halves. Divide both sides by 100 first. So this is 0.75. Because this is e and you want to get to x, take a natural log of the left side equals natural log of the right side, or write it as a log. Either way, this is what you get. So ln of the left side is 0.75 by the way, is negative 0.4x. So what is x? The left side divided by negative 0.4. Again, this is exact, and we change the division by negative 0.4 as negative 2.5. I hope you realize 1 over negative 0.4 is negative 2.5, because it's the same as 10 divided by 4 with a negative. Now, if you multiply these two using a calculator, this becomes positive because ln of 0.75 is negative. This is an approximation. We used a lot of decimals. If they said 1, 2, 3, 4, 5, 6, then you look at 7 and you do the rounding. That's why you want to keep the exact answer if possible. Could you read this question for us, please?
Liz deposits $10,250 into an account that earns 4% compounded interest. How much will the account have at the end of 10 years if it is compounded monthly? A of t equals P times the quantity 1 plus R over N to the NT. How much will the account have at the end of 10 years if it is compounded weekly? How much will the account have at the end of 10 years if it is compounded continuously? And what is the doubling time? A of t equals P e to the RT.
Thank you so much. So we are looking at compounding. Remember the basic interest. I equals PRT. When it gets compounded, we use this formula. Therefore, take a look at the formula we are going to write. P, the principal, is 10,250. Rate is 4% or 0.04. And T is 10. So this is T, this is R, this is P. Okay, we have this. Now in part A, how much will the account have at the end of 10 years if it is compounded monthly? N is the number of compounding that takes place per year. So if it's yearly, N is 1. If monthly, N is 12. So we are going to replace it with 12. And I hope you realize at this point, you really have to use a calculator, add these two numbers, raise it to the power of 120 times this number. There you have it. For part B, weekly, N is 52. N is 12 here. N is 52. And again, you plug it into a calculator accordingly. So how much is it if it's continuously? We are using this formula. We plug in, and it's a tad more than each and every one of them. And with that being the case, we want to see what is the doubling time. So we, regardless of how much we have, it so happened that it's 10,250, but whatever the amount is, it really doesn't matter. It's a matter of, the importance is about the rate. So you change it to 2p because you want to double it. You drop the p and you get 2. Now you take a natural log of both sides. ln2 equals RT, and T becomes ln2 over R. By the way, if for any reason, if R is missing, ln2 divided by T. In this case, R is given as a 0.04, plug it in, and it takes a little bit more than 17 years to do the doubling, pH equals negative log H plus, where H plus is the hydrogen ion concentration in moles per liter. We want to find the pH for the solution whose hydrogen ion concentration is 3.45 times 10 to the power of negative 4. Would you be kind enough to read this part for us? The pH represents the measure of acidity and alkalinity of a solution. A number between 0 and 7 indicates acidity. Lower numbers indicate stronger acidity. A number between 7 and 14 indicate alkalinity. Higher numbers indicate stronger alkalinity. According to this scale, a value of 7 represents neutrality like water. It is roughly the negative of the log to base 10 of the molar concentration measured in units of moles per liter. Hydronium ion concentration, we show it with H plus or H3O plus. So pH by definition is simply this. Now, as far as you're concerned, all you have to do, just you plug in to a calculator and multiply by negative. That's your answer, and you're done, and it's okay. But even without a calculator, I want to show you, even if you don't have a calculator, roughly what you have, and this is what you have. If you were to do it even without a calculator, you separate the two. This one, negative 4, sits in front because it's a log of 10 to the power of negative 4. You apply the negative. Now, this is positive 4. This is negative log of 3.45. You know, log of 10 is 1. So this one is a little bit less than 1. So the result of these two, when you add them up, must be between 3 and 4. So it's less than 7, and it's acidic. Even without the calculator, you should be able to estimate that and have an idea what you're dealing with. Here's another word problem. A nuclear reactor contains 200 grams of radioactive plutonium, P239. It decays according to the following formula: A equals A sub 0, e to the power of minus 0. We have 4 zeros and then 284 T. How much will it remain after 5,000 years? And we want to find the half-life. So basically, you replace the T with 5,000. So the formula, replace the T with 5,000, where A sub 0 is given as 200. Using a calculator, after 5,000 years, from 200 grams, what is left? 173.52, and you use the same units. Now, as we did with doubling, we do the same thing with the half-life. You can go and deal with the general format. Half-life, that means whatever the initial amount, we have half of it left. So you don't even have to know what the initial amount is. A sub 0 cancel out. If you take a natural log of both sides, the right side becomes just the exponent. Ln of the right side is just the exponent. Now the left side is ln1 minus ln2. ln1 is 0. So it's minus ln2 over minus 0.0000284, which, using a calculator, gives us 24,406.59 years.